Oops. So yeah, as before, I have some slides. So you guys see the slides perfectly?
Yes.
Perfect. So yeah, last meeting we sort of discussed the first part of this chapter, which was about defining a general notion of a derivative of a map between two vector spaces, x and y, and to recall that this meant we can define the derivative as basically a map from x to a linear map from x to y. Uh, this linear map being bounded, and we saw some examples, and as discussed, it's not the only way to define a derivative on vectors between these vector spaces, but it's one of the most useful, especially since if you want to do anything about, okay, you have a function that takes in a matrix and returns maybe something a matrix or a vector, it's really the right notion of a derivative for that. But whenever you're dealing in function spaces, things can go wrong, and then you may have to uh, twist your notion or use a different notion of derivative to get what you want. But here we were still in the nice and gentle part. And after that, we saw that if we have some kinds of optimization problems on function space, like a control problem, like finding the shortest path between 2 points among all the possible curves, then that's a optimization problem, and we found that there are the usual optimality conditions. So the derivative being 0 here, the 0 map, plus your functional, so the function you're trying to minimize being convex. That is enough to show that you have a local, global minimizer or optimizer concave instead. But generally, solving these kinds of problems directly by uh, computing the derivative and trying to find a stationary point is pretty not easy. So what we'll be seeing today is first off a way to turn a very broad class of these functional minimization problems into differential equations, which are maybe not necessarily easier to solve, but they are at least easier, usually slightly easier to solve, but it's not always the case that you can find solutions. And of course, if your functional is not convex, then you can have multiple different solutions with problem being stability. And really, this approach is actually the secret sauce behind modern physics. So pretty much all of modern physics can be restated into this framework, and actually is. So I mean, I'll be landing into more into the physics side today to provide evidence as to why this approach is very nice. I also asked Stable Diffusion to give me its impression of the main subject of today, so the Euler-Lagrange equations. This is one of the images came up with that came up the nicest, so maybe we come back to this, but sort of, I like it because it sort of captures the idea of these Euler-Lagrange equations being like very fundamental to physics. So I have more images at the end, but I thought it would be a nice touch. So uh, enough of the introductions. Given the base idea of these Euler-Lagrange equations is that if you have a functional equation, so you have functional f of x where x is some function, here we assume it's a curve, it could be a surface or a function defined on the two-dimensional space, and so it's x here is a function, and your functional is defined as an integral on some interval of this big F that depends on x, on the derivative of x, and maybe the point at which you're integrating. And the big theorem of the chapter section rather, that stationary points, so points that are local optima of this functional here, they must satisfy the so-called Euler-Lagrange equation, which is stated as taking the partial derivative of big F relative to its first argument and minus taking the partial derivative of x relative to the second argument to the prime, deriving that by t, and this equation must be equal to 0. Note that these functions here may not necessarily live in a, or at least the function you're exploring, you're minifying over, don't have to be a vector space here, but there is a way to actually get back to a proper functional derivative, which is what I have here. So if you have, say, a candidate stationary point of your base functional, you can actually consider the space of perturbations around it, so the Banach space, defined as, say, if we have a one-dimensional function here, the space is the space of functions that are continuously differentiable over your interval, such that their endpoints are 0. What that allows us is that because the endpoints are 0, this set definitely contains the 0 function, so it is in fact a function space, and moreover a Banach space in this case. And when I say perturbation, we mean that we have this f from our vector space R, which is just original functional applied to x star or candidate solution plus h. So it's really a perturbation. And you can imagine, let's say you are trying to find your solution, and x prime is your candidate solution, and h is just a perturbation. So you start out maybe from A, and it's the same point, and maybe you're able to deviate, but at the end you have to be back at the same endpoint. So maybe you're trying to find a curve between points xa and xb, and you're trying to minimize either the length or the energy it takes to get there, then h would be how much you swivel around your solution. And using this, because this f tilde is a functional map from x, which is a Banach space, to R, then we can take its derivative, and x star is a stationary point of f if the derivative of f tilde, here I'm using the more standard notation for the functional derivative at 0, so 0 here being no perturbation, the derivative has to be 0, so I have a stationary. And I have a first example, which goes back to what I showed last time of trying to find what is the shortest path between 2 points here in the Euclidean norm. So I first have my space of curves between differentiable curves in Rn, such that they must start at xa and they must end at xb, and then define my length functional as just the integral of the norm of the derivative, which is the standard way of defining the length of a curve. And if you apply the Euler-Lagrange equations to this, note that the Euler-Lagrange equation you don't have to explicitly construct your Banach space. You can just construct the Euler-Lagrange equations and get your equation. So this equation basically said that the derivative of the ith component of the gamma prime over the norm of gamma prime must be 0, and one particular solution is to say, okay, this must mean that the derivative of the above side must be 0, so it must be a constant. And if the derivative of your curve is a constant, that must mean it's a linear function. If you use then the sort of boundary conditions, you can find the following curve, which is just the linear interpolation between xa and xb. And I was a bit surprised by this, because I would expect that if you have a curve that stays on your straight line or line segment, but maybe you move at different speeds, it should still be a solution. But apparently here it's not the case. Maybe dig deeper. But that's sort of okay, we can use this to solve our problems, but really the original setting in which these Euler-Lagrange equations or formulated and motivated about physics. So I guess most people here will have at least seen the Newtonian mechanics, so that if you have, say, a point mass particle with a mass m subject to some force F, then we can use Newton's law to describe the motion of the particle. So F equals the ma. Here ma, so q, I'm assuming, is the position of my particle, then q prime is the speed and or velocity, and q prime prime is the acceleration. And we see that we can reformulate all this using the Euler-Lagrange equations, and that it's actually usually very beneficial because we can do a lot more than just the Newtonian mechanics. For example, given some one is here, it's the one-dimensional trajectory q, we can first define the potential energy of this trajectory by v being the integral starting from some x0, which can be arbitrary, of the force along that trajectory. The force it takes to, excuse me, we're integrating the force from our starting point, which is arbitrary, to the point x we are. So it's basically, it's the same way as we define, let's say, the gravitational potential as the mass times the gravitational constant. It's the amount of work you have to do starting from x0 to get x against the force. But really a more telling definition of the potential is just that its derivative is the force. So when we say that, we say, okay, the force derives from a potential, and really the potential can be defined up to a constant, right? Just take right here with the derivative, so we have v plus a constant, it doesn't matter, and that's why we can choose this and initial point arbitrarily. And then we can also define the kinetic energy as sort of the mass times the velocity squared divided by 2. And then the sort of the general physical principle is the principle of stationary action, that says if we define the action of our system as the integral from our initial time to the end time of this function L of our position and velocity at the time, which is called the Lagrangian of the system, and here is just the kinetic energy minus the potential. And the principle of stationary action says that the motion q of the particle is a stationary point of the action if so the actual motion of the particle is a stationary point of the action. So what this says actually is that the action is, you can sort of think of it as the energy of your trajectory of your movement. And what the principle of stationary action says is that nature tries to minimize the energy spent to do anything. So one of the first instances of this was saying, okay, light always takes the shortest path, and this was somewhat famously used back in Newton's time by it was Bernoulli to find the solution of the so-called Christochron problem. So we find the curve such that you can slide it on the shortest time. And actually Bernoulli used this, so the idea of that, okay, light always takes the shortest path to find its solution. And he thought it was very clever, and pestered Newton about it, who didn't appreciate the challenge posed by the youngster. And to get from the Euler-Lagrange equations back to the classical Newton equation, we can just express actually the Euler-Lagrange equation of our system. So we have the derivative of the potential minus the derivative of the time of the kinetic energy. I think actually I missed, yeah, this should be a D, it should be a 2. Sorry for the typo, but yeah, you can easily see, because it's only the potential that depends on the position, and the kinetic energy only depends on the velocity. Then so if you apply that mechanically, this is the general Lagrange equation you get for classical mechanics. And if you then reuse the fact that this is just minus the force, then we actually recover Newton's law. And a first example is using that to express at least the equation of a two-body problem. So if you have, say, a body of a very large mass m, so maybe the sun, and you try to find the orbit of a smaller body of mass m, maybe the Earth, and you express this in polar coordinates. So r is the distance between the smaller and the larger body, and phi is the angle around it. Then we have this action to describe the energy of our system. Again, um, sorry, this here is again the kinetic energy, and these two, or at least this is the potential, and this is the kinetic energy again, which I may have forgotten to square again. Sorry. And if you apply the Euler Lagrange equation to this, you get this, and you get these two equations, with the bottom one being actually one of Kepler's law. So one nice thing that we see already, and this is more of a general trend, is that using this Euler Lagrange equation, you have a tendency to recover sort of conservation laws or stuff that stays constant in your system, and these are very useful because you can use it to simplify a problem, right? Because you know this is constant, so you, okay, this quantity is constant, but sort of puts a constraint on it. And imagine using this to reduce the dimensionality of your problem space. And I mentioned before that this was really the secret sauce behind physics, and I really meant it, because beyond classical mechanics, most of modern physics, you can frame it in terms of the stationary action principle. For example, I have here very not nondescript Lagrangian for electromagnetism. So electromagnetism, you can derive it in terms of Lagrangian mechanics. General relativity, same thing. You have the kappa here would be the curvature, and r would be a tensor describing the geometry, and so Lm is for the accounting for the matter in your universe. So general relativity, you can solve it with the, well, maybe not solve it, but you can describe it with the Lagrangian viewpoint. Same thing if you're trying to find orbits, say light, that just again trying to find the shortest path. Same thing for quantum mechanics, although with a big star, that quantum mechanics is a bit more special. So the key takeaway here is that Lagrangian mechanics really does provide a unifying language for physics, and really, like, I have this little meme image of this just having this very three-step process of writing down the Lagrangians and solving the Euler Lagrange equations, then profit. But of course, not every Lagrangian is very palatable. So, for example, this wall of text is actually the Lagrangian of the standard model. So it's standard model being elementary particle physics. So I can see it's a very large amount of quite a few equations. So obviously finding solution to this is not going to be very easy. So even though you can express the equation, that doesn't mean finding the solution super easy either. A last point, and I think then it's pretty much the end, is that there is a very real sense in that the symmetries of the Lagrangian, so your Lagrangian is invariant under translation or rotation, for example, that gives rise to so-called conservation laws, so conserve quantities over the trajectory. So, for example, to express the energy of your system being the sum of the kinetic energy and the potential energy, then taking the time derivative of that is constant, so we know that the energy is conserved. And another example from classical mechanics is if you have your Lagrangian that does not depend on the position, then okay, the equation here is a bit porky, but what he called the momentum, being the mass times the velocity, is also conserved. And this is a straightforward calculation. And a very generic expression of this is so-called the Noether theorem. So Noether was one of the very earlier, at least, one of the first women mathematicians. She, I think, She was around about 1 century ago, and she was very famous for her theorem about clarifying what it means to have this link between symmetries of the Lagrangian, so symmetric under translation, under rotation, and whatever, and finding conserved quantities that correspond to that. So again, some very fundamental here. As a side note, but we won't get it to that today, but the chapter does, that beyond the Euler Lagrange equations, you can further refine this into so-called Hamiltonian mechanics, which is just a refinement which can get you easier equations, but the key message here is that these Hamiltonian mechanics are like the very fundamental in quantum mechanics. So, for example, the Schrödinger equation, which is like the fundamental equation, or at least one of the fundamental equations in quantum mechanics, is actually just the Hamiltonian. Yeah. All I have left is some further stable diffusion images of the Euler Lagrange equations, and we can start the discussion.
Great, thank you. Yeah, I just wanted to add that yeah, the principle of stationary action is like really, really, really big in physics. Like that generalizes much further than like Newtonian mechanics. So that's like yeah, as you were saying, it's very fundamental.
Yeah, I think my favorite example of it, if you're trying to find the shape of bubbles, so soap bubbles, maybe like constrain them with some wire, then that's also because you just have to say, okay, the bubbles trying to minimize their surface tension, and then can easily express well, easily with big quotes, express the solutions that.
Yeah, like if you wanted to sort of write down the truth of the universe, like how does the universe work? I think like what you would write down is like stationary action, Noether's theorem, and Euler Lagrange, essentially.
Yeah, I mean, doing these slides and reading the chapter, it sort of got me thinking of maybe potential links between that and some of the stuff that actually done in machine learning. For example, I mentioned, okay, we're trying to minimize this, so maybe there are people trying to actually use the Euler Lagrange equations to optimize their neural networks. I don't know. Sounds very evil to do, but
Does variational inference have anything to do with calculus of variations, or are these
I
completely
think
separate?
so. Yes. So quite probably that would have be a link. But I think maybe one of the more useful takes, perhaps for machine learning, would be this whole Noether theorem stuff, because practice when you have an invariant like that, that means you can sort of reduce the dimensionality to your system. You can because you have additional constraints of what your solution can be. You can that means some of the variables and unknowns can be fixed, or at least expressed in terms of other unknowns. So you have a slightly simpler problem. And I think at least it reminds me of how, for example, when you take a convolutional network and you want to be a translational invariant, then automatically that means weight sharing, which is also another instance of this symmetries of your desired solution that impose some constraint and dimension reduction.
Yeah,
There's a good
I would.
oh, sorry, go ahead.
Go ahead. Okay, so I was just gonna add that I think like the goals of like equivariant deep learning and I think the new term that they're using is like geometric deep learning with
Yeah.
Taco Cohen and Michael Bromstein, I think is, I can't remember how to spell his last name, but the UK. I think they're also tied to DeepMind, but they have this idea that Michael is calling like the Erlangen program for deep learning. The
Right, right,
Erlangen
right, right,
program
right.
being like this overarching, broad, geometric view. Like a program with a capital P in mathematics is like an overarching goal to like map and explore an entire subfield of mathematics. There's the Erlangen program, there's the Langlands program, there's probably a few other programs that I'm not aware of. But it's like, a massive effort of hundreds of mathematicians to map out every little niche and nook of mathematical subfield, and to map out its connections to other fields. And the Erlangen program was, I don't know the full history of it, but basically, kind of 100 to 150 years ago, maybe even as early as 200 years ago, they were starting out like trying to map out all of the sort of geometric principles. It might actually even have concluded earlier than, or more recently than that. I don't know if it's concluded yet.
I don't think it
But
has. I know it's been going on for a while, but I don't think. I think it's been like. I think the main idea was to explore the connections between um, geometry, but also stuff like algebra and topology, and
mhm,
such a huge field that I don't think they've quite completed it.
right, and so Michael's idea of trying to do like an Erlangen program for deep learning is basically trying to map out like all of the interesting like geometric quantities. Like here's this talk I'll share, where he basically lays down like the idea of the program, because these programs start by like someone giving like an impassioned lecture and getting a whole bunch of people on board to do it, um, to lay out like the plan, let's say. And it's basically to map out like all of a lot of the Erlangen program in mathematics was kind of like studying symmetries in geometry, and like because geometry with like a capital G is like often turns down to this inspecting these spaces in the of geometric spaces, like projective spaces, or uh, you know positive symmetric spaces, and um, all of these different like geometric spaces, and then mapping out all of their symmetries and like the Lie groups that act on them and things like that. And then each of the Lie groups that act on it symmetrically have like a conserved quantity, Noether's theorem, and basically just mapping out all of these symmetries. And the idea of doing that with deep learning is like each of these symmetric ideas kind of corresponds to a neural network architecture that you can kind of map out, and well, maybe a family of neural network architectures that instantiate that idea, and kind of retracing the steps of all of the mathematicians in the Erlangen program and applying all of the symmetrical ideas that they've mapped out from that to neural network architecture design, and understanding like when should you use a graph architecture, when should you use uh uh like equivariant network, and all these different ideas, or a convolutional network. um yeah, so I'll link the
I think I saw a talk maybe in the same series about, okay, if you have a problem and you want, okay, I want such and such symmetries, how should I design my network? I think that's sort of the end goal, is to have, okay, here's my problem, I want to have this set of symmetries, how do I design my network?
Right. There's a whole series of lectures on these on YouTube.
I think I saw a few of them.
Yes. I'm curious
Okay.
whether you can kind of go the other way, like try to mine like figure out what symmetries your data set has without having to like pick an architecture a priori.
Yeah, I think the problem, if you assume you have noise, then your problem becomes instantly more
Yeah.
difficult.
You're trying to find out what symmetries you almost have.
yeah, approximately equivariant.
I mean, yeah, it's one of the things. I think definitely this more geometric deep learning is certainly one of the parts of deep learning that attracts maybe more math and physics people. Like I definitely like the manifold hypothesis, and I like to think about, okay, I assume that my data lives on a manifold. What can I find out about that actual manifold? But if you have noise, then it becomes instantly more difficult. Anyway, I think Kazumi has a sort of question about, so it's one of the lemma used to prove the Lagrange equations, which is more or less used to show that if you have one functional
So H
that's,
is like a test function here in this
yeah, it's
equation, right?
basically a test function.
So
Basically
any
a
test
lemma that
function
shows,
has
okay,
a higher property than
function behaves like
K plus
this
P
has
plus
to be
Q.
constant. Does anyone have questions about the slide, by the way, or can I stop sharing my screen?
Go for it.
Wait, I do have a question though.
Go on then.
Hold on. I just noticed that the textbook theorem 3.5 is an if and only if statement.
Correct.
So I was thinking like if the Euler Lagrange is just like a first order characterizations of a stationary point, then how does it address the saddle point problem?
That's definitely, yeah, that's pertinent question, is that in practice you don't really know if you have a saddle point or not. I think in the exercises in the same part, you sort of rely on, okay, I have a stationary point, and if I want to show that it's a minimizer, then I have to prove that the function I'm minimizing is convex. And in the first exercise, because the norm, it's relatively easy to show that. I think but they show on the exercise involves multiple different norms. Yeah, slightly above. So the first exercise, for example, is in the Euclidean plane, because we have integrating this function which is convex, then the functional is convex. So when you have a stationary point, it's a minimizer. But the 3.15, for example, given your constraints, it's actually a concave function. So the stationary point to find is actually a maximizer. But yeah, in practice, you don't really, you can't really tell if you have a saddle point, a maximizer or minimizer.
Right.
And in practice, when solving these Lagrange equations for physical systems, you can get any of the two. But generally, you try to find the minimizer bit, because those would be your stable solutions, whereas a maximizer would be a unstable solution. Same thing for for a saddle point.
Got it. Yeah, that was my question. Yeah.
So did that answer your question? I didn't quite hear you.
Partially, yeah. I have to dig into the map to see how that worked though.
Yeah, I think the biggest problem here because you don't really have access to. You can try to compute the second derivative, but it's one much harder, and you can do the old trick of, okay, I look at the Hessian and look at its eigenvalues. If they're all positive, then it's a minimizer. If they're all negative, it's a maximizer. And some of them are positive and negative, that it's a saddle point. And unfortunately, that doesn't really work in the general case.
You're not gonna calculate the infinite dimensional Hessian?
I mean, first off, good luck trying to compute. It would be a function that maps a point x to a linear map from a linear map to y.
Well, certainly. I mean, I don't whether or not the book goes into it. I'm sure someone has defined a notion of the like second and higher order derivatives for
Yeah,
functionals, right? I mean,
defining is relatively easy. Computing them is significantly harder, I think.
I've got to go. Thanks all.
Yeah. Bye.
thank you.
And besides, because it's an infinite functional, then you have to do spectral analysis of that, which is again much harder. Yeah, I think unless we're out of, we have still questions for now, we can go.
Sounds good. Thanks again for setting this up. This was nice.
Yeah, no problem.
Making
So
slides and everything.
I think with my current schedule, it will have to be 2 weeks again. So for now, yeah, so back to the 2 weeks interval where we'll be entering into chapter 4, so on Hilbert spaces. I'll keep you guys posted with that.